Hi folks, I'm Mr. Fullerton, and today's topic is the photoelectric effect, an effect we see with electromagnetic radiation that leads us to believe that electromagnetic radiation, light, has both a wave and a particle nature. Our objective for today is to calculate the energy of a photon from its wave characteristics. So to begin with, one of the problems that scientists had was seeing that electromagnetic radiation, or light, could strike a metal and it may emit electrons, which we call photoelectrons. Now, not all electromagnetic radiation creates these photoelectrons, though. And shining more light, higher intensity, brighter light, doesn't give you a higher likelihood of getting a photoelectron. What gives you a higher likelihood of a photoelectron is shining a higher frequency of light, a more energetic light beam. So this was a problem scientists were struggling with toward the beginning of the 1900s. Now, the smallest possible pieces of electromagnetic radiation, or light, the particles of light, we call photons. They have zero mass, zero charge, and their velocity in a vacuum is c, or 3 times 10 to the 8 meters per second. The energy of a photon, again, comes in discrete amounts. It's quantized, and you can calculate the energy of a photon using the formula h, which is known as Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times the frequency, or, since frequency is c over wavelength, it's hc over lambda. So sample problem 1. A photon of light traveling through space with the wavelength of 6 times 10 to the minus 7 meters, or 600 nanometers, has how much energy? Well, E equals hc over lambda. We know c, that's a constant, h is a constant, and we're given the wavelength. So that's just going to be 6.63 times 10 to the minus 34 joule seconds times 3 times 10 to the 8th meters per second, the speed of light in a vacuum, divided by our wavelength, 6 times 10 to the minus 7 meters. And don't forget, when you plug this into your calculator, put parentheses around anything you divide by. That should give us an answer of around 3.3 times 10 to the minus 19 joules. All right. The spectrum of visible light emitted during transitions in excited hydrogen atoms is comprised of blue, green, red, and violet lines. What characteristic of light determines the amount of energy carried by a photon of that light? Is it its amplitude, frequency, phase, or velocity? Well, recall that the energy of a photon is given by its frequency. Higher frequencies, higher energy photons. Correct answer must be number 2. Number 3, determine the frequency of a photon whose energy is 3 times 10 to the minus 19 joules. Well, if energy is Planck's constant times frequency, then we can figure out that frequency must be energy over Planck's constant, or 3 times 10 to the minus 19 joules over 6.63 times 10 to the minus 34 joule seconds, which gives us 4.5 times 10 to the 14 1 over seconds, or hertz. Let's take a look at one more here. The graph represents the relationship between the energy and the frequency of photons. What is the slope of the graph? Well, if you recall, the slope is going to be rise over run. Our rise is in energy of a photon. Our run is in frequency. Well, if E equals hf, then that means the slope, E over f, must be equal to h, or Planck's constant. So the slope of this graph is h, 6.63 times 10 to the minus 34 joule seconds. So, this problem with photoemission, photoelectrons coming from metals, was theorized and worked on by Albert Einstein, and he actually won the Nobel Prize for his work here on the photoelectric effect. He theorized that the electrons in the metal are held in a sort of energy well. They're bound to the atom by some amount of binding energy, the energy well energy. The electrons must absorb at least that much energy to get out of the well in order to become free of the metal, in order to be photoemitted. The electrons had to absorb this energy from a single photon. 2 photons with half the energy needed to get out of the well wouldn't do it. It had to be absorbed all at once. So the photon that was absorbed had to have at least as much energy as the binding energy, the energy that was holding that electron to the atom. The amount of energy holding the electron to the atom, the depth of that energy well, so to speak, or the amount of binding energy is known as the work function of the metal. And then any excess energy absorbed beyond that needed to free the electron became the kinetic energy of the electron. So once it's free, any extra energy becomes kinetic energy of the electron. It gets translated into speed. Another way to put it, if we look at this flow chart, a photon strikes a bound electron. If the energy of the photon is greater than the electron binding energy, or the work function, then the electron absorbs that photon and any excess energy is turned into kinetic energy. If the energy of the photon isn't greater than the electron's binding energy, you don't have enough energy in that photon, its frequency is too low, then the photon isn't absorbed. Nothing happens. So let's look at a sample problem here. The alpha line in the Balmer series of the hydrogen spectrum consists of light having a wavelength of 6.56 times 10 to the minus 7 meters, 656 nanometers. Calculate the frequency of this light. Well, that's pretty straightforward. V equals F lambda, our wave equation. If we want frequency, then frequency must equal V over lambda, and the speed of light in a vacuum is 3 times 10 to the 8th meters per second, divided by its wavelength, 6.56 times 10 to the minus 7 meters, for a frequency of 4.57 times 10 to the 14 hertz. Now B says calculate the energy in joules of a photon of this light. Well, there we can use E equals hc over lambda, or we could have used hf since we now know the frequency. That's 6.63 times 10 to the minus 34 joule seconds times 3 times 10 to the 8th meters per second divided by its wavelength, 6.5 times 10 to the minus 7 meters. Plug all that into your calculator. Don't forget parentheses around the denominator. You should come up with about 3.03 times 10 to the minus 19 joules. And part C then asks, determine the energy in electron volts of a photon of this light. So we need to convert the energy from joules to electron volts. All right, we have 3.03 times 10 to the minus 19 joules. We want that in electron volts. So I know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. My joules will make a ratio of 1, or effectively cancel out. And when I run this through my calculator, I come up with about 1.89 electron volts. Let's take a look at one more problem, putting it all together. A photon of electromagnetic radiation strikes a metal. The metal has a work function of 2 electron volts. If the emitted photoelectron has a kinetic energy of 2 electron volts, what was the wavelength of the photon? Well, it took 2 electron volts to free the photoelectron, and it then has 2 electron volts of kinetic energy. So the photon that came in must have had a total energy of 4 eV. Now, we want to figure out what its wavelength was. So the first thing I'm going to do is I'm going to convert that energy into our standard unit of energy, joules. So I know electron volts in joules, and 1 eV is equal to 1.6 times 10 to the minus 19 joules. My electron volts make a ratio of 1. 4 times 1.6 times 10 to the minus 19 joules is 6.4 times 10 to the minus 19 joules. Now that I have that in joules, I can use the formula E equals hc over lambda to solve for my wavelength, because wavelength then will be hc over my energy, or 6.63 times 10 to the minus 34 joule seconds, times 3 times 10 to the 8th meters per second, over my energy in joules, 6.4 times 10 to the minus 19, and I come out with a wavelength of about 3.11 times 10 to the minus 7 meters, or 311 nanometers. Hopefully this gets you started with the photoelectric effect. If you have questions, need more help, check out aplusphysics.com. Thanks and make it a great day.